Good day everyone, I am Carl Christian Malesa, and for now we will be discussing about the four applications of first order differential equations. And I was assigned to discuss about the first two applications of first order differential equations. So without any further ado, let's get started. So the first application of the first order differential equation is the orthogonal trajectories. Orthogonal trajectories. Any curve which cuts every member of a given family of curves at right angles is called an orthogonal trajectory of the family. It is not necessary that the curve should intersect every member of the family. But if they intersect, the angle between their tangents at every point of intersection is 90 degrees. So orthogonal means perpendicular to each other. And if we say orthogonal trajectories, we have a point of intersection which is 90 degrees or right angle. So we have here the four steps. I have here four steps or four procedure to find the orthogonal trajectory. So the first step is let f of x, y, c is equals to 0 be the equation of the given family of curves, where c is an arbitrary parameter or an arbitrary constant. So the second step is differentiate the family of curves and eliminate c to form a differential equation. Third, substitute the negative reciprocal of dy over dx, or we have the negative dx over dy for dy over dx in the above differential equation of the orthogonal trajectories. Last step or last procedure is by solving this differential equation, we get the required orthogonal trajectories. So for us to have more knowledge or to gain deeper understanding with regards to orthogonal trajectory, I will be showing to you one example of how to find the orthogonal trajectory. So we have here, find the orthogonal trajectories of the family f of curves given by y squared is equals to cx cubed, where c is an arbitrary constant. So we have here the solution. The first step is identify the given family of curves, which is y squared is equals to cx cubed. Then the second step is differentiate the family of curves. Then we get, so we will differentiate y squared is equals to cx cubed. Then we get 2y dy dx equals 3cx squared. So we will divide both sides of the equation by 2y in order for us to get to only have dy over dx on the left side of the equation. So we have dy over dx is equals to 3cx squared over 2y. So since we are going to eliminate c here because we are looking for the orthogonal trajectory, so we will find the value of c. So how to find the value of c? So just simply solve the value of c in the equation y squared is equals to cx cubed by dividing both sides of the equation by x cubed in order for us to get the value of c. So by dividing y squared is equals to cx cubed, dividing both sides of the equation by x cubed, we get our value of c, which is equals to y squared over x cubed. So just simply substitute the given value of c, the calculated value of c in the equation, so we get dy over dx is equals to 3x squared over 2y times the value of c, which is equals to y squared over x cubed. So multiply, we get our value of dy over dx is equals to 3x squared y squared over 2yx cubed. Since the equation 3x squared y squared over 2yx cubed can be simplified to its lowest term by using the rule of exponent. So we get our value of dy over dx, which is equals to 3y over 2x. So now let's proceed to the third steps. If any curves intersects orthogonally at point xy, then we must have here dy over dx is equals to the negative reciprocal of the dy over dx, which is equals to negative dx over dy. So since we have already solved the value of dy over dx, which is equals to 3y over 2x, so just simplify the reciprocal of dy over dx. So we get dy over dx is equals to negative 2x over 3y, and that is the value of our the value of the negative reciprocal of the dy over dx. So we are here now in the last step. So we will now solve the above differential equation, which is dy over dx is equals to negative 2x over 3y. So next is we will separate the differentials and then multiply both sides of the equation by y. So we get y dy is equals to negative 2x over 3 times dx. So next is we will integrate the left-hand side of the equation with respect to x. With respect to y. And then the right side of the equation with respect to x. So we get the integral of y dy is equals to the integral of negative 2x over 3 dx. So next is we will evaluate the integral. So we get y squared over 2 plus c is equals to negative 1/3 x squared plus c. So since both constants of integration are arbitrary constants, we will replace them with the constant c. So we get y squared over 2 is equals to negative 1/3 x squared plus c. So next is we will multiply both sides of the equation by 2. Y squared over 2 is equals to negative 1/3 x squared plus c multiplied by 2. So we get y squared is equals to negative 2/3 x squared plus 2c. Since the expression 2c is a constant, it is possible to denote that the whole expression as a constant c. So we get y squared is equals to negative 2/3 x squared plus c. So just simply transpose the equation. We get c is equals to 2/3 x squared plus yc, plus c is equals to 2/3 x squared plus y squared is the orthogonal trajectory of the family of curves given by y squared is equals to cx cubed. So now, let us proceed to the second application of the first order differential equations, which is the rectilinear motion. When we say rectilinear motion problems involve the movement of an object along a straight line. So the position of the rectilinear motion is described by a function x of t, where t represents time. So I have here 4 steps for solving rectilinear motion problems involving position using derivatives. So we have here the step 1, which is if you are finding the displacement of the object over the interval or AB, evaluate x of b minus x of a, where x of t is the position function. If you need to find the distance traveled by the object, follow steps 2 through 4. So which is our step 2 is to find the total distance traveled. First, find the velocity function, which is represented by v of t is equals to x prime of t, or the derivative of x of t, or the derivative of the position function. So the step 3, find where v of t is equals to 0. This is where the object changes direction. So the last step, or the step 4, divide the time interval into subintervals that will separate the two different directions of motion using the results from step 3. So find the total distance traveled by finding the absolute value of the displacement of the object in each subinterval and adding the results. So for us to have representation or to have more idea with regards to rectilinear motion, I will be presenting to you one example about rectilinear motion problems. So we have here the example. If the position of a particle is described by the position function, x of t is equals to t squared minus 5t plus 6, where t is greater than or equal to 0, is in seconds, and x of t is in inches. Find the displacement of the particle over the first 5 seconds. Then find the total distance traveled by the particle at the same time. So we have here the solution. The first step is we will find the displacement over the first 5 seconds. So we need to evaluate x of 5 minus x of 0 is equals to t squared minus 5t plus 6 minus t squared minus 5t plus 6. So since we are looking for the displacement over the first 5 seconds, we have x of 5. So now, just simply substitute the value of t in the given equation. So we get x of 5 minus x of 0 is equal to 5 squared minus 5 times 5 plus 6 minus 0 squared minus 5 times 0 plus 6. So simplify. So we get x of 5 minus x of 0 is equals to 25 minus 25 plus 6 minus 0 minus 0 plus 6. So we get 6 minus 6. So we have our value of x of 5 minus x of 0 is equals to 0. So the step 2 is we will find the total distance traveled. So first is find the velocity function, which is denoted by v of t is equals to x prime of t. So here we get v of t is equals to the derivative of the x of t. So we have here our derivative of x of t, t is equals to t squared minus 5t plus 6. So the derivative of this position function is equals to 2t minus 5. So that is why we get our velocity function here, which is equals to v of t is equals to 2t over 5. So now, the third step is we were going to find the v of t is equals to 0. This is where the object changes direction. The velocity is equals to 0 when v of t is equals to 0. So 2t minus 5 is equals to 0, and then transpose negative 5 to the right side of the equation. So we get 2t is equals to 5, and then divide both sides of the equation by 2 in order for us to find the value of t. So by dividing both sides of the equation by 2, we get our value of t is equals to 2.5. So that is our value of t. So for the last step is we are going to solve, since the particle changes direction after 2.5 seconds, we have two subintervals to use to determine the distance. So the first one is from 0 second to 2.5 seconds, and the second subinterval is 2.5 seconds to 5 seconds. So now we will going to find the absolute value of the displacement over the interval. So we have here the absolute value of x of 2.5 minus x of 0 is equals to the absolute value of 2.5 squared minus 5 times 2.5 plus 6 minus 0 squared minus 5 times 0 plus 6. So then simply simplify the equation. So we get the absolute value of absolute value of x 2.5 minus x of 0 is equals to the absolute value of 6.25 minus 12.5 plus 6 minus 0 minus 0 plus 6. Then solve. So we get here the absolute value of absolute value of negative 0.25 minus 6. So subtract. So we get the absolute value of negative 6.25. So therefore, the absolute value of x of 2.5 minus x of 0 is equals to 6.25. And this is the displacement of the particle over the interval of 0 second to 2.5 seconds. So now we will be solving the second or the next subinterval, which is from 2.5 seconds to 5 seconds. So now we have here the absolute value of the displacement. The absolute value of x of 5 minus x of 2.5 is equals to the absolute value of 5 squared minus 5 times 5 plus 6 minus 2.5 squared minus 5 times 2.5 plus 6. So simplify the equation, we get the absolute value of quantity 25 minus 25 plus 6 minus the quantity of 6.25 minus 12.5 plus 60. So now simplify, we get the absolute value of 6 plus 0.25, then add, so we get 6 absolute value of 6.25. So therefore the absolute value of x of 5 minus x of 2.5 is equal to 6.25. So that is the displacement of the particle from 2.5 seconds to 5 seconds. So therefore, the particle traveled 6.25 inches between the interval of 2.5 seconds and 5 seconds. So our displacement is 0 inches. 0. Why? Because there's no changes in the two subintervals. Since our displacement value or the displacement of the particle from 0 second to 2.5 seconds and the displacement value of the particle from 2.5 seconds to 5 seconds is still the same, which is 6.25. So we have here our total distance traveled by the particle at the same time is 12.5 inches because we just add the displacement value from 0 second to 2.5 seconds and the displacement value from 2.5 seconds to 5 seconds, which are 6.25. So we will add 6.25 plus 6.25 is equals to 12.5 inches. So that is the total distance traveled by the particle. So I think that is my part about the applications of the first order differential equations, which are the orthogonal, trajectories, and the rectilinear motion. So I hope that you've learned my discussion about the orthogonal, trajectories, and the rectilinear motion. So thank you for listening.